Question 12 wants us first of all to look at oxidation states. So in this reaction, wants the oxidation states of the sulfur. So remember that oxygen in compounds is -2, unless it's a peroxide, which these are not. So we've got 2 lots of -2 there. And the sum of oxidation states is 0, unless it's got a charge, but it hasn't. So this has got to add up to 0. And therefore, since 2 lots of -2 are -4, the sulfur is +4. So we got that one. And then we can do the same for SO3. So 3 lots of -2 from the oxygens takes us to -6. Again, it's 0 overall, so if that's -6 to 0, we need +6 to balance it up. So you can see the sulfur's been oxidized from +4 to +6. And then in the second reaction, you add water to SO3 to make sulfuric acid, and we can do the same thing with that. So this time we've got 4 lots of -2, takes us to -8, and 2 lots of +1. Okay, so we've got -8 plus 2 is -6. Again, it's got to equal 0 overall, so the sulfur has got to be +6. So you can see in that second reaction where we add SO3 to water, the sulfur stays the same, so that's not a redox reaction. The first one is, but that one isn't. And then it tells us that the catalyst for this reaction is V2O5, and it asks us for the systematic name of that. So the issue there is that vanadium is a D-block element, and remember that D-block elements in general can have different oxidation states in compounds, so you can't just call it vanadium oxide, because that would be ambiguous. So it's going to be called vanadium something oxide, and the something is the oxidation state of the vanadium. So again, we just do the same thing. Say this time we've got 5 lots of -2. So that takes us to -10. It's 0 overall because there's no charge. So -10 to 0 means the vanadiums add up to +10, and there are 2 of them. So that's 2 lots of +5. Okay, so that's the oxidation state of the vanadium, and that's what goes into here in the form of a Roman numeral. So it's vanadium 5 oxide is the name of the compound. Next we're moving on to looking at this equilibrium. So it gives us a value for the equilibrium constant at 700 degrees C and some information about a particular mixture. So first it wants the expression for Kc. So remember, the stuff on the right goes on the top. So it's the concentration, because it's Kc rather than Kp, concentration of SO3 squared, because there are 2 of them, divided by the stuff on the left. So concentration of SO2 also squared, and then times the concentration of O2. Okay, so that's our Kc expression. Now this mixture, it says, may or may not be at equilibrium, and the way we can tell is by computing the value of this expression and seeing whether it equals Kc, because we know what Kc is, it tells us there. And if we compute that value and it equals 2.8 times 10 to the 2, that's great, we're at equilibrium. If it doesn't equal that, it just means we're not at equilibrium. So the one thing you have to be really careful about is that these numbers you're given are moles, they're not concentrations. And you've always got to watch out for that, because you can't just plug moles directly into that expression. So you've got to turn them into concentrations first. And that's very easily done, because you just use concentration is moles over volume in dm cubed. And because the volume is just 2, that's very easily done. So you get 0.250 moles per dm cubed for SO2, 0.05 moles per dm cubed for oxygen, and 0.35 moles per dm cubed for SO3. So it's not difficult, it's just remembering to do it. That's the important thing there. So you can then plug those numbers into that expression. Now remember, that may not equal Kc, so when we do that, don't write Kc equals that, because it might not. So we can just write the expression, SO3 squared over SO2 squared times O2 is equal to, and then we put the numbers in, 0.35 squared over 0.25 squared times 0.05. Okay, we put all those numbers in, crunch them together, and what comes out is 39.2. And that will be same units as Kc, moles to the minus 1 dm cubed. And you can see that doesn't equal Kc. It's a much bigger number, so that should be 10 to the minus 2, should it? No, it is 10 to the 2, right, that's fine. So, right, let's just redo that bit. So you can see then that by comparing that with Kc and saying, yeah, that's not the same, we can deduce that we're not at equilibrium. Okay, so we just write that down, that that does not equal Kc, so it's not at equilibrium. Okay, but again, you need an explicit statement of how you know that. Okay, so don't just get the number and say, so you're not at equilibrium, because they'll say, how do you know? So you calculate the number and you say that doesn't equal Kc, so it's not at equilibrium. And then it asks us to go a step further and say, well, which way would it have to go in order to reach equilibrium? And to do that, you just look at how this number compares with what it should be. And you can see it's too small. 2.8 times 10 to the 2 is 280, so our value is too small. So you say that the value needs to increase to reach Kc. Okay, because it's got to go from 39.2 up to 280. And then you do the top line, bottom line kind of argument to explain how it's going to do that. So in order to increase the value, the top line has to get bigger and the bottom line has to get smaller. And it's worth just saying that explicitly, just so that it's clear what you're thinking. So that means that the top line will increase and the bottom line will decrease, because that will have the desired effect of making the answer bigger, and eventually it will get big enough that it equals 280, and then you're there. And you say, right, well, how do we increase the top line? Well, the top line is the concentration of SO3, so we need more SO3. Decrease the bottom line, we need less of those things, so the reaction will move in the forward direction. Okay, in order to achieve that, so the reaction will go in the forward direction to reach equilibrium. Okay, the next job is just to calculate delta S using those molar entropies. So we just remember that delta S is equal to the entropy of the products, because we're gaining the products, so we're gaining their entropy, minus the entropy of the reactants, because we're losing the reactants, they're being destroyed in the reaction, and therefore we're losing their entropy. So we can just put the numbers in. So the entropy of the product is 2 lots of SO3, so 2 lots of 256. And then the reactants are being lost, so that's 2 lots of 249. For the 2 SO2s, and we're losing 205 for the oxygen. Okay, so it's plus these and then minus all of those. And if you crunch those numbers, you get 512 minus 703, if you work that lot out, which comes to minus 191 joules per Kelvin per mole. Okay, so that's come out to be negative, and of course that's what we would have expected, because these are all gases, so we're going from 3 moles of gas to 2, So decrease in the moles of gas, that should indeed be minus a negative number, as it is. Next job then, having calculated delta S in the last part, we've got to calculate delta G at 500 degrees C. So, as always, begin by writing the expression. Delta G is delta H minus T delta S. And we've got all the numbers, so it just comes down to plugging those in. So we get that equals minus 197 for delta H, and then minus T, 500 degrees C, add 273 to turn it into Kelvin, is 773. And then delta S is minus 191 joules per Kelvin per mole, but it's got to be in kilojoules per Kelvin per mole to be compatible with this number in kilojoules per mole. So we've got to divide that by 1,000. So it's 773 times minus 0.191. Okay, and again we've got this awkward subtracting a negative number, so it's probably sensible to just rewrite that as minus 197 plus 773 times 0.191. Okay, because if you subtract a negative number, that's the same as adding a positive number, and if you work that out, you should get minus 49.4 kilojoules per mole for delta G. Okay, is your answer. And then we're asked to say what that tells us about the feasibility of the reaction. And the point is, remember that delta G needs to be negative for a reaction to be feasible. So don't just say this means it's feasible, because you've got to explain what is it about that number that shows you it's feasible. So you say delta G is negative, and that tells you that the reaction is feasible. At 500 degrees C. The next thing it wants us to find is the temperature at which delta G equals 0. So we can find that because, remember, our definition of delta G is delta H minus T delta S. So if delta G equals 0, we can say delta H minus T delta S is equal to 0 at this particular temperature. So delta H is equal to T delta S. Okay, just moving that term over to that side. And a simple rearrangement tells us that delta H divided by delta S is then equal to T. Okay, so that's the expression that we're going to use to find this temperature. We've just got to plug those numbers in. So we've got minus 197 for delta H. Delta S has got to be in compatible units because that's in kilojoules per mole. This needs to be in kilojoules per Kelvin per mole, and therefore it's not minus 191, it's minus 0.191 is the number that goes into there. And it's a negative divided by a negative, so you get a positive answer, which it must be, because the absolute temperature must be positive, and that comes to 1031 Kelvin is the answer. And but on the answer line it asks for it in degrees C, so we get 1031 minus 273 is how you convert Kelvin into degrees C, and that comes to 758 degrees C. So then it asks us for the significance of that number, and you can see we worked out that at 500 degrees C delta G was negative, so the reaction was feasible at 500 degrees C, but when we take the temperature up to 758 it's just now tipping over to becoming not feasible. So we can look at this temperature dependence in terms of a graph. You don't have to draw this, but it's just a good way to think about these things in general. So if you imagine a graph of delta G against the absolute temperature, so this would be absolute 0 up there, and this is delta G is 0, then from this expression, you know that at absolute zero, when t is 0, this whole term will vanish, because 0 times anything is 0. So therefore delta G is equal to delta H at absolute 0, which is minus 197. Okay, so it's minus 197 there. So it's very negative, and therefore very much feasible at absolute 0. And we also know that at 500 degrees C, it's still feasible, because delta G was still negative when we calculated that. But when we reach 758 degrees C, which is 1031 Kelvin, it reaches 0. So what we've got is this situation where it becomes gradually less negative, and at this temperature, which as we say is 1031 Kelvin, that's where it equals 0, and you can see that's the cutoff point, because at all temperatures above that, delta G becomes more and more positive, and so from that temperature onwards, positive delta G means that the reaction is not feasible. Okay, so the answer to the question is the significance of that temperature is that that's the highest temperature at which this reaction is feasible. So you wouldn't have had to go through all that drawing the graph. The way to sort of quickly realise that is to say, well, we know that at a lower temperature at 500 it was feasible, and therefore it must be that this is the cutoff beyond which it stops being feasible. So you could sort of work all that out quickly without going through the graph, but this is the best way to really understand it. This last part is just a basic mole calculation. It's got nothing to do with all the entropy and free energy stuff, and it's just saying, if we get 10 kilograms of SO2, what's the maximum amount of sulfuric acid we could get? In other words, what's the theoretical yield if we had no losses along the way? And so all you do is to realise that for each mole of SO2, you get a mole of SO3, and then the reaction of SO3 with water to make it H2SO4. Again, each mole of SO3 gives you a mole of H2SO4. So however many moles of SO2 you start off with, you should get that number of moles of SO3, and however many moles of SO3 you should get that number of moles of H2SO4. In other words, if we know the moles of SO2, that's the same as the moles of sulfuric acid we should get. So we just work that out. Moles of SO2 is equal to mass over mR. And it tells us to use 32 for the atomic mass of sulfur rather than 32.1, but I think they'd let you use either. So we can say that's 10,000 over 64.1, because it's SO2, is the mass of SO2, which comes to 156.0 moles of SO2, which means that we should get 156.0 moles of H2SO4 is the theoretical yield. And then we just have to turn that into a mass. So mass is moles times mR, which is 156.0 times 98.1, or 98 if you use the rounded value, which comes to 1534 grams. But it asks for the answer in kilograms, so we have to, 15340 that should be. So that's the number of grams, so we have to divide that by 1,000 to put it in kilograms, okay, which is 15.3 kilograms. Okay, so that's the maximum amount of sulfuric acid that we should expect to get.